Okay, so this is going to now be our final video in the series, and we will finish the proof for why it is that when you add up all the digits of a number and check to see if it's divisible by 3, whether or not it'll be divisible by 3 will be the same as if the whole thing was divisible by 3. And we did an example of that in the first video. So today, before we get there, I just want to talk about the last little thing we need, and that's the idea of a decimal expansion. So really, all a decimal expansion is it's just kind of a way to write a number as the sum of basically powers of 10. So if I take 578, just as an example, I can write this as basically 5 times 10 squared plus 7 times 10 plus 8. So this is always a good way to, anytime you're dealing with digits and you want to figure out what the sum of the digits are, it's always best to maybe write it like this. And you can verify this is basically 500 plus 70 plus 8. So maybe I'll just write this is 500 plus 70 plus 8. And hopefully you recognize that that is 578. In general, it looks like this, which, yes, I know it looks like a big mess, but really, just if you have this is an n plus 1 digit number, because we have the 0 here. Basically, I can write it as the first digit, the nth digit, this is and then take it to the n, the power 10 to the power of n, and just add them all up, just like I did up here. So this is just the general version of what you see up there. Okay, so finally, we're ready to look at the proof of this thing. So the first thing that we're going to do is basically take whatever our number is and basically write it out as a decimal expansion. So really, if it's 573, we would do it like we did in the last one. But this works for any digit. We can always write this expansion. So this is like this is the ones place here, and then this would be the tens place, and so on all the way up for a particular number. And then let's see what happens when I take the remainder of a big number like this, modulo 3, or basically that's when I say modulo, I mean we're taking the remainder when we divide by 3. Well, because of our theorems that basically say that this can interact with sums and products, what we're allowed to do is we're allowed to basically bring this modulo inside of everything here. So where I'm really interested in bringing it inside here is that I can basically take each of the powers of 10 modulo 3. So maybe just to do a quick example, if I wanted to do 500 and 18, for example, modulo 3, what I can do is I can basically take 5 times 10 modulo 3 to the power 2. Okay, and then plus 1 times 10 modulo 3 to the power 1 plus 8. Okay, and the key to ultimately why this is true, probably the most important thing that we learn about this, is ultimately because if I take the number 10 and I divide it by 3, I get a remainder of 1. Let's think about why that's true. Basically, we've got, 3, we've got another 3, we've got another 3, and then we've got a plus 1 to give us 10. So we got 3 groupings of 3, and then 1 more, and that gives us 10. So basically, when we reduce this, and we find that our remainder modulo 3, I basically can take all of the powers of 10, all the 10s here, and basically replace each of these guys here with a 1. Well, why is that useful for us? Well, it's useful because basically what we end up getting is we just end up getting the sum of the digits. That's what this is, modulo 3. And that basically completes our proof. Now, again, this might be very confusing, and you might need to look at this and read it and do maybe a couple examples of it and to see why something like this would work. But the key is actually a little bit more than what we said here. What we're really saying here is that if I have a decimal expansion for something and I divide it by 3, it's going to actually have the same remainder. So it's not just that an integer is divisible by 3 if the sum of its digits is divisible by 3. It's actually stronger than that. Basically, the remainder of the sum of the digits is the same as the remainder of the original number when you divide by 3. This is actually why, in our example, when I took this thing, which is not divisible by 3, and we got a 0.3 repeating, that's basically going to be a 1/3. If this was modulo 3, this would be equal to 1. Well, if I do it with the sum of the digits, and I do that modulo 3, I also get 1. So that actually covers both directions. Again, hopefully you found this to be somewhat satisfying. I guess maybe just a last note on why this works for 9. Well, really, it's the exact same proof, simply because if I take 10 modulo 9, I also get 1. So every place here where you see a 3, just replace it with a 9, and it works the same way, and we get the same rule about remainders. So again, I find this to be interesting, and again, it probably will take quite a bit of time maybe to understand it, but I hope you found it interesting. And this is ultimately what makes math interesting, is trying to come to a little bit of an understanding. So take care, and I hope you enjoyed this.